Hello everyone. Today we'll start a discussion on statistical thermodynamics or statistical mechanics. But since this is not a course on statistical thermodynamics, we'll just keep our discussion very brief, and we'll only learn few basic concepts in statistical thermodynamics, which will help you to understand the reaction dynamics in a better way, because we'll be using those formulae or the relationship to understand how reactions work. So the most important thing we are going to discuss here, how to calculate partition functions, and we'll limit our discussion up to there. Now I'll give you a general introduction, again not going into too much details, that how you should think about the statistics, or how the Boltzmann statistics was developed. Now when around in 1880 or so, when Boltzmann actually showed this Maxwell's distribution of molecular speed or molecular energies can be actually derived from, if you assume that any matter is composed of molecules, and if you just talk about the statistics of those molecules, you can derive the entire thing. Now the idea of what Boltzmann was nurturing in mind is something like molecules have energy levels, although he will show these energy levels as discrete energy levels like we use in quantum mechanics. But in original Boltzmann's derivation, those energy levels are considered to be continuous. Now again, I am not going to derive the Boltzmann distribution here. You can actually refer to any standard textbook. For example, you can have a look at the physical chemistry textbook by Atkins. There he has Atkins and De Paula, they have actually derived the Boltzmann distribution law. We just discuss the salient features and how what are the conceptual understanding of the Boltzmann distribution. Now what it tells is that the way we think about it, it is, again, it's not the original way that Boltzmann distribution came, but it is the way we think about Boltzmann distribution today. Suppose we have some energy levels in the molecule. Take a very simple system. Let's say some molecules are there, some particles inside a box. Now particle in a box energy levels are of course not the way I have drawn it. It's not equispaced, but suppose the molecules have some equispaced energy level. For example, vibrational energy levels are like that, and suppose these energy levels have energies like this, 0 epsilon, 2 epsilon, 3 epsilon, something like that, 4 epsilon, and so on. Suppose we have 4 particles in our system. So we have a system, and system means it's a macroscopic system, in the sense that whatever we measure in classical thermodynamics, as we emphasized many times, that classical thermodynamics is a macroscopic science without any detail of the microscopic understanding of the nature of the matter. Now it is very much phenomenological science, and people derived very nice relationship before 1850s or so, or around 1850s when Clausius did his monumental work. But so according to macroscopic thermodynamics, you can actually define the total energy of the system. And suppose we are also saying that my system, the macroscopic system, is composed of some number of particles, but the number of particles is also fixed. So macroscopically I have two parameters, total number of particles and the total energy of the system. And suppose I have the total number of particles, which I am writing as let's say capital N. Let me just write it as this. And then also I am saying that my macroscopic system has another definition, and let me just write it in a slightly different region for a reason. I will just write some distribution here. So suppose I have n is the total number of particle, and now what is this n? Suppose these energy levels I am writing as say I am saying that what is the energy of the ith energy level. So I denotes for 0, 1, 2, 3, something like that. So if the energy of an arbitrary level I is epsilon I, then and if the number of particles in that level is Ni, then I can say that the capital N, the total number of particles, is nothing but the number of particles in the ith energy level, and then you sum over all the energy level. And that we are taking, let's take a number, let's say it is 4, I have 4 particles. And also say that the total energy, sometimes we write it as E, sometimes we write it as U, it's the total internal energy. And what that will be in terms of summation. Suppose if I have Ni particles in the level epsilon I, so the energy contributed by those particles will be Ni times epsilon I, because each particle has an energy epsilon I in the ith level, and there are Ni particles in the ith level. So the total energy will be Ni into epsilon I for the ith level. So for the total system, I will have to take a summation over that, and let us also take a number for that. Let's say that is 2 epsilon. So that is the description of my macroscopic system, that I have 4 particles and the total energy is 2 epsilon. Now microscopically the system might have different configuration, and that is what is interesting and what we are going to discuss right now. So what do you mean by configuration? Let us give you an example. Suppose I have these 4 particles, and these 4 particles I have to arrange in such a way in these energy levels so that the total energy is 2 epsilon. Now how can I do it? One easy way is that I can keep one particle, let's say here, in the energy level 4 epsilon, and all 3 particles I can give at energy level 0. So you can see from this equation the total energy will be 1 particle in 4 epsilon level plus 3 particles in your 0 energy level. So that is nothing but 4 epsilon. I think we took 2 epsilon. Let us just take the total energy to be 4 epsilon, then we will have more number of distribution. Now the question is it an unique number, in the sense that is it how many ways you can actually achieve this particular distribution. Now it depends now whether these particles, these 4 particles, are indistinguishable or distinguishable. Meaning, suppose I have 4 particles like which I can label them, like I have particle 1 which I am labeling as A, and particle 2, particle 3 and particle 4, and I can actually label them as A, B, C, D, or some let's say some color, red, green, blue and black, whatever, so that I know actually which particle is which. I mean, it has a specific identity. So in this case I am also assuming that the particles are distinguishable, and this is very, very important. Distinguishable. If the particles are distinguishable, meaning we can distinguish or separate or segregate one particle from any other particle, then I can actually say this distribution, the way I have written it, that 3 particles in energy 0 and 1 particle in energy 4 epsilon will have many distribution. Why? Because this one particle can be the particle A, this can be the particle B, this can be the particle C, and this can be the particle D. Meaning, when I am choosing the A particle in energy level 4 epsilon, B, C and D are in energy level 0. When I am choosing particle B in the energy level 4 epsilon, then A, C and D are in 0, something like that. So the number of ways I can actually choose one particle in energy level 4 epsilon and 3 particles in energy level 0 is nothing but 4. So what I am showing vertically is basically the distribution, and here I am basically writing the number of possible ways we can achieve this particular distribution. Now these possible ways means actually number of microstates. So what is a microstate? Now microstate means actually a specific distribution that the system has, which is a microscopic distribution of the system. However, has to satisfy the macroscopic distribution, which is the total number of particles are 4 and total energy is 4 epsilon. Now let us say, can we actually have some other distribution? Of course, there are many distributions. For example, I can actually put two particles in energy level, let's say 2, and then the total energy will be 2 into 2 epsilon, and to keep the total energy 4 epsilon, I have to keep the other 2 particles in this other energy level, so 0 energy level. So then again I will get the distribution as the same, the macroscopic description as the same. So what I am showing here, I can actually make a table like thing. So this is another way of distribution. So in the first distribution I kept 3 particles here, 0 particle here, 0 particle here, 0 particle here, and 1 particle there. In the second distribution I have kept 2 particle here, 0 particle in energy level epsilon, 2 particles in energy level 2 epsilon, and for other cases I am keeping 0. Now how many ways I can achieve this distribution? Then again you have to think, if the particles are distinguishable, I am choosing 2 particles in energy level 2 epsilon. What are these 2 particles? It can be AB, it can be AC, it can be AD, and then it can be also BC, it can be BD, and it can be CD. So the total numbers are basically 6. Now how do I get this 6 mathematically? It's a very interesting thing. So it's a very easy thing if you have studied permutation and combination. So I had 4 particles and I am choosing basically keeping them in picking up 2 at a time. So that is nothing but the number 4C2, which is factorial 4 divided by factorial 2 into factorial of 4 minus 2, which is 2. So 2 factorial is 2, 2 factorial is 2 here, and 4 factorial I can write it as 4 into 3 into 2 into 1 and divided by 2 into 2, and thus you can see that these 2 cancels and then it gives me this number 6. That's how we get this 6 mathematically. So there will be 6 such states. Now you see that moment I choose for the 2 particles for state 2 epsilon, the other 2 particles in the 0 are automatically chosen. So so it is very straightforward. Now similarly you can actually have other distributions. For example, if I have 4 particles, there will be one distribution that all the 4 particles will be in in energy level epsilon, but that will have just number 1 because it's just an unique distribution. And similarly, I can also have many other ways. You can think about it like I can put 3 particles in energy level 3 epsilon, and I can have 1 particle in energy level here. Then again, there can be many different distribution. You can think that that 1 particle in the 0 energy level can be chosen in 4 different ways. It can be A or B or C or D. So it will have number 4, something like that. Now what we see is very interesting, that number of microstate, since the particles are distinguishable, that is changing from one distribution to the other distribution. So if I ask you that what is the probability of having what is the number of molecules or number of particles in an arbitrary energy level EI, which is basically Ni, how do you calculate it? So then you say that, okay, so I can actually, it can vary, but what on statistical ground, if I have a huge number of particles and sufficiently large amount of energy so that I can have many possibilities, then you can argue that that distribution will be most probable, which has the maximum number of microstates, provided all these microstates are equally probable, in the sense that, so what we are saying, suppose we have a macroscopic system and the total number of microstates which correspond to that particular macrostate, which is defined as a fixed number of particles and fixed internal energy, that I can achieve in many different ways. And then suppose just take a number, suppose there are 100 microstates totally available to our system. Now, out of these 100 microstates, I find that there are suppose a distribution, there are suppose 3 distribution that I can have, that I can actually have these microstates, and one distribution has suppose 60 microstate, and the other distribution suppose has 30 microstate, and the third distribution has suppose 10 microstate. Just the way we have drawn it, that this is the vertically we have a distribution, and that has 4 microstate, this has 6 microstate, this has 1 microstate, and this is 4 microstate, something like that. And this number will continue, of course, because we have not considered all the possibilities. There are many other possibilities also. So you can now say that that distribution will be most probable which has maximum number of microstates, because all microstates are equally probable, because all microstates satisfy this number, which is the total macroscopic to satisfy the macroscopic description of the system of these 2 constraints, that my total number of particles and total energy is fixed. Now, in this way, what we do in statistical thermodynamics is, the first thing, you actually calculate the distribution or the most probable distribution, and the most probable distribution is by definition is that distribution which actually has maximum number of microstates. So again, a microstate is basically a microscopic description of the system. So different microstates correspond to the same unique macroscopic description. So one macroscopic system can have internally many microstates, because many microstates correspond to the same physical macroscopic properties. Now, how do you do it? So basically you derive, which you are not going to show, you derive a general equation how you can get the number of microstates for a specific distribution, and then you just take the derivative with respect to the change in particle, and then you make it to be 0, because you are actually maximizing the number of microstates to find which is the most probable distribution. And then you do a very generalized way, in the sense that I will just give you a flavor. Suppose what I am saying here is that suppose the energy levels I am denoting as 1, 2, 3, something like that, 4, and I am saying that I have chosen N1 particles for energy level 1. So this N1, N2, in general the Ni has to be figured out, and then I'm choosing N2 particles energy level 2, then N3 particles for energy level 3, N4 particles for energy level 4, something like that. And so then if the total number of particles is fixed, then I can say that how many ways I can choose I can fill in the first energy level, and then you can easily say by combination that okay, fine, I can choose it in N, C, N1 different ways. Once you do that, the second energy level or can be for that actually this N2 can be chosen in how many ways. So once I have chosen N1 particles, I am left with N minus N1 particles, and out of those many particles I can actually choose N2 particles to fill in the energy level 2 and so on. So the total number of distribution or total number of microstates for that particular distribution, where I have N1 particles in energy level 1, N2 particles in energy level 2, or in general Ni particles in energy level I, will be something like that. And you can actually easily do that. So it will be n factorial by n1 factorial into n minus n1 factorial. The second thing will be n minus n1 factorial divided by n2 factorial into n minus n1 minus n2 factorial. That way we will proceed, and you will easily figure out that these factorials will get cancelled, and so ultimately at the end of the day what you will get is something like this, which is n factorial divided by n1 factorial into n2 factorial into n3 factorial, something like that. And then you can actually so that will be basically the total number of microstates in that distribution. If I just call it as something like that sigma d, d suppose is the distribution, a general distribution, then the way you derive it is that you will maximize this number, but instead of taking the maximization like the differential of this sigma d with respect to ni, making that to be 0, we actually take if that is correct, we instead of taking the distribution function directly, we take the logarithm of the distribution function and make that to be 0, because there are you can easily see that if I use the logarithm of this thing, then you can actually write the logarithm of n factorial and use something known as Stirling approximation, and in the denominator you see that it's a logarithm of many numbers n1 factorial into n2 factorials. Then actually you can write it as a summation, because log of a into b into c is log of a plus log of b into plus log of c, that way. And then you use Stirling approximation and many other things with the constraint. What is the constraint? That my total number of particles is fixed, and also the total energy is fixed. And then you use something for any differential equation with a constraint, means actually if you have many variables in the differential equation, suppose I have a system of variables, like I have x1, x2, x3, something like that. In this case also these variables are basically the number of particles that I am varying per energy level. So the ni I am varying. So what is interesting here, keeping the total n constant, so what is interesting here is that if I do that, then I say that I cannot do it independently, because all these system of equations are not linearly independent because of this constant. So there is something called Lagrange method of undetermined multiplier. So that you apply, and then you basically solve the differential equation, and then ultimately at the end of the day you can actually calculate these ni for any general distribution, and you can show that this ni is basically proportional to, or we can take a fraction that what is basically the probability of having some number of particles in energy level I, that will be basically the number of particles divided by the total number of particles. So that is nothing but ni divided by sum over ni, and that ni from all this derivation you will see that that is given by a Boltzmann factor, which is nothing but scaled by the energy, exponentially scaled by the energy, and then you get expression like this, where the beta this is given as 1 over the Boltzmann distribution times the absolute temperature. Now this derivation is given the way I have told you, after you use all these two constraints as well as the Lagrange method of undetermined multiplier. So then you get this distribution function. Now what the important quantity we see here is this quantity, which is sum over e to the power minus beta epsilon I, and that we call as a partition function, or you denote it as q, and this will be our starting point of discussion, and because this is the key thing that we are going to use most heavily. We are going to calculate this partition function for many systems, for any energy levels. So we define this, we call this as a partition function, or better the way I have shown it, it is better to call it as a molecular partition function, because actually we started with the molecular energy levels and then derived this partition function. There are also other ways of thinking about it. You could actually think about the entire system and then entire macroscopic system, and you could actually derive the statistics in a very different way from an ensemble approach, where we actually say that okay, fine, I have many different microstates, and then if I measure at a time, say for example at an instant, then I can find the system in one of these microstates. If I measure it in a different time, then I can think that okay, the system has a different microstate, something like that. So meaning if you just go back to our previous discussion, suppose I have this system which we just discussed, composed of 4 particles which are A, B, C, D, which are distinguishable, and the total number of particles are n, and the total energy is E or U. And then what we are going to see here is that if we have let us say measure the microstate of the system at an instant, and suppose I do a measurement right now, and I find that one A molecule or A particle is in energy level 4 and the 3 all other in energy level 0. Now, the next instant somebody else does a measurement and finds that okay, C and D are in particle in energy level 2 epsilon, and the other 2 are in 0. Then I come back and do the measurement again. Suppose I again find something like distribution 1, particle in C in energy level 4 epsilon and all others in 3, which means actually the system, the macroscopic system at different time is going through different microstates. So, at an instant it has a particular microstate, but this microstate it is changing. So, the system is time evolving. The question is, what will be the average property of something? Let us say I talk about energy, or total energy here is fixed, or say something like say entropy of the system, which are average quantities. So, then I have to take the average over, I have to take a time average over all these things. Now, the question is, if I want to do a time averaging, then I have to solve a dynamical equation. If the systems behave classically, then I have to do a classical solve a classical equation motion, because I need to know how these energy levels are being changed, how the particles are moving from one energy level to another energy level, or some other quantum mechanical time dependent Schrodinger equation or something like that. But that is a very tedious exercise, because in general this is not actually any macroscopic system is not just composed of 4 particles, it is composed of millions and billions of molecules. So, or atoms, and for a finite energy you will have so many possibilities. So, you cannot just do it, rather you say that okay fine, the time average of all this of the system which is traversing through different microstates over time is as if taking an ensemble average. Now, what is an ensemble? The ensemble is a thought process. It is basically a hypothetical collection of the system corresponding to different microstates, but that which actually is a collection of different microstates of the system, but which correspond to the same macrostate. Meaning, as if you are thinking that okay, so I have a collection of macroscopic system, all macroscopic system for which the total energy and total number of particles is fixed, and then I am saying that the macrostate is evolving through different microstate is conceptually equivalent to saying that I have different systems with different microstate which correspond to the same macroscopic state. But then what I will do is that I will just do the statistics of all this system, because suppose the probability of having a microstate where actually I have one particle in energy level 4 epsilon and 3 particles are in 0. So, that will be weighted by this number. So, there is a statistical weightage for each such distribution, and then you do the statistics of those things, and then you conceptually say in this case actually since energy and the number of particles are conserved, these macroscopic systems are not exchanging energy with respect to each other. And in a more general situation, we actually say that okay fine, these systems are not actually isolated system, but the temperature is constant, but the energy is constantly fluctuating between them. Then we talk about it, then we call that kind of ensemble as a canonical ensemble, and the one which I gave the previous example is called a microcanonical ensemble, and in that way you can actually do a ensemble approach on the statistical mechanics, which was put forward by Willard Gibbs. But we do not need to know all these details, because what we will be doing is just restrict our discussion to this molecular partition function, and we will show how one can calculate this molecular partition function for different problems, for different say energy levels. That is what we are going to do now.